Hello everyone, welcome to the day 22 or the lecture 22 of the machine learning teach by doing project. Today we are going to learn about a very important technique in regression which is called as ordinary least squares method. This technique will help us to find the hypothesis that minimizes the squared error. Yesterday, we started looking at linear regression and we learnt about two things. We learnt about the hypothesis for linear regression, which is just straight line in 2D, a planar surface in 3D, etc. And it's given by theta transpose x plus theta naught. We also looked at the loss function which we are going to use, which is simply the square loss. Now we will look at the fourth step in the machine learning framework. We looked at the first three steps, which is data, generating hypothesis, and loss function. Now the fourth step is formulate the ML problem as an optimization problem and find the best hypothesis through optimization procedures. So that is exactly what we are going to do. We are going to formulate this machine learning problem as an optimization problem. Now, you might find several courses offering lectures on ordinary least square. The main issue with these courses is that they directly start from the matrix or the matrix form of the OLS, but they don't show you how exactly to go step by step to the solution by doing a hands on demonstration. So, very similar to everything which we do in this course, we will start with a very practical hands on demo, and you yourself will reach the solution. That way, ordinary least square will be very intuitive to you. After you yourself find the solution for the hands on demo, then we will look at the matrix form. And then we will see the similarities between the matrix form and what we have obtained. Uh, if you have some basic knowledge of linear algebra, it will really help in this lecture. But if you do not have, it's fine. Portions which you do not understand, you can go back after this lecture and learn that particular portion of linear algebra, which will be very helpful to you. So let's get started. First of all, as I mentioned, we are going to immediately start off with a hands on demo. Let me expand the screen a bit. Okay, so we are going to immediately start with a hands on demo here. So here's the problem. I have 4 points in the x1, x2 plane, and these 4 points look like this. The first point is 1 comma 2, the second point is 2 comma 3, the third point is 3 comma 5, and the fourth point is 4 comma 4. My aim is to find the best hypothesis uh, or the best straight line y is equal to um, theta 1x plus theta naught. Find the best y which minimizes the square loss for all these data points. Now imagine you exist in a world where you do not know about ordinary least square. You just have knowledge of the fact that you want to convert this into an optimization problem. Think about what you will do. Okay, first thing what you will probably do is think of the objective function which you need to minimize. So the objective function j will have two parameters, theta 1 and theta naught. These are the two parameters. So okay, this should be theta naught here. These are the two parameters for which you need to optimize for. Um, because once these two parameters are fixed, the hypothesis is fixed. So the hypothesis is given by the average 1 by 4, since I have 4 data points. Summation of I goes from 1 to 4. Guess minus actual square. Correct? It's as simple as that. Um, and what will my guess be? My guess will just be the hypothesis prediction. And in yesterday's lecture, we already looked at the hypothesis. It looks something like this: theta 1 x1 plus theta naught. So then this value will be, guess minus actual square will be theta 1 into xi plus theta naught minus yi square. I hope you understand what this means. Here we are just taking the guess minus actual whole square for all the points and we are adding it together. Basically, what we are doing is, let's say we have a hypothesis, uh, and the true value is known, which is yi. So for the first point, I find the guess, subtract the true value, and square it, which is my loss function. I do this for all these 4 points. So remember that, let's say if I'm looking at this particular point, the x value is 2, correct? So let us look at the guess and the actual. So where it hits this hypothesis, that is my guess, and what the actual value, that is a. So then the loss for this particular point will be g minus a whole square. We are just summing up this particular difference or this loss for all the data points and then dividing by 4, because we are taking the average. So now your task is, this is the objective function and we don't have a regularizer term, so it is just the loss function here. We want to find theta, we want to find theta 0 and theta 1, which minimizes j. So we want to find theta 0 and theta 1 which minimize this objective function. Now imagine if you have any function out there. Let's say if you have a function y equal to x square and you want to find that x naught which minimizes y. What do? You take the derivative and set it equal to 0, right? This is exactly what we are going to do now. First, let me write the loss function in detail. It looks something like this. Uh, by detail, I mean I'm just going to sum it up for all the 4 points. So it's going to look like j of theta comma theta naught will be equal to 1 by 4 theta 1 x1 plus theta naught minus y1 whole square plus theta 1 x2 plus theta naught minus y2 the whole square plus theta 3 x3, sorry, this should be theta 1 into x3, theta 1 into x3 plus theta naught minus y3 square plus theta 1 into x4 plus theta naught minus y4 whole square. Now we want to find the optimal theta and theta 0 and theta 1, right? So all we need to do is we need to take the derivative dj, divide dj of d theta 1 needs to be 0 and dj by d theta naught should be equal to 0. Ideally, we should be calling these as partial derivatives, but I'm just using a simple framework here so that you understand what is going on. So we need to optimize two parameters, correct? We need to optimize theta 1 and theta 0. So similar to what we did for this function y equal to x square, we took the derivative. But now there are two parameters which need to be optimized. So we need to make sure that the derivative with respect to these two parameters will be equal to 0. And those will be our optimal theta 0 and theta 1 which minimizes j. There is one more consideration here, that you might be thinking that what if this is a maxima? It could also be something like this, right? Why does it have to be a minimum where the derivative is 0? So usually you need to find the second derivative there, and you need to show that the second derivative is greater than 0, but I'm not going to do that. It turns out that the second derivative is greater than 0, and what we indeed find is a minimum. So the theta 0 and theta 1 which we get after setting these derivatives to 0 are indeed the theta 0 and theta 1 which minimize j. So now all we need to solve for is we need to solve for derivative with respect to theta 1 equal to 0 and derivative with respect to theta 2 equal to 0. Let us see what the derivative. So now I'm going to replace this by partial derivative symbol. Let us see what the derivative with respect to theta 1 is. So the 1 by 4 will remain just like that. What is the derivative of this quantity? This quantity, if you take the derivative with respect to theta 1. Remember the chain rule. First, you imagine this is just x square and you take the derivative. So it will be 2x. And then you have to take the derivative of whatever is inside with respect to theta 1, correct? So the only thing which will remain is x1. So the derivative of this entire quantity with respect to theta 1 turns out to be 2 times x1 into theta 1 x1 plus theta naught minus y1. What I have done is I have just applied the chain rule here. So you first treat that this is y equal to x square. So the derivative is 2x. So that's where this 2 comes from, and that's where this thing comes from. Now you have to take the derivative of what's inside with respect to theta 1. What is inside is theta 1 x1 plus theta 0 minus y1. Derivative of theta 0 and y1 with respect to theta 1 is 0 because they are not dependent on theta 1. The only thing remains is this, and the derivative of this with respect to theta 1 is x1. That's why x1 comes here. Similarly, for all other quantities, if you take the derivative, it's just this theta 1 x2 plus theta naught minus y2 plus 2x3 theta 1 x3 plus theta naught minus y3 plus 2x4 theta 1 x4 plus theta naught minus y4. Correct? This is the derivative. Um so let us simplify this further. What we want is that we want to set this equal to 0. So what this will help do is that, so let's take this 2 outside, 2 by 4. Let me bring theta 1 common, theta 1 x1 square plus x2 square plus x3 square plus x4 square plus theta naught into x1 plus x2 plus x3 plus x4 minus x1 y1 plus x2 y2 plus x3 y3 plus x4 y4. This quantity needs to be equal to 0. And remember, we have the values of x1, x2. So x1 is 1, x2 is 2, x3 is 3, x4 is 4, y1 is 2, y2 is 3, y3 is 5, and y4 is 4. So let's plug in these values here and let's see what we get. So setting this equal to 0 implies that theta 1 x1 square plus x2 square plus x3 square plus x4 square plus theta 0 x1 plus x2 plus x3 plus x4 minus this whole quantity, which is 2 plus 6 plus 15 plus 16 is equal to 0. So the first equation which we have is 30 theta 1 plus 10 theta naught minus 39 equal to 0. This is the first equation which we have, and let me highlight it in pink. This is the first equation which we have, which we obtained because dj, or partial derivative of j, with respect to theta 1 is equal to 0. Now we also need to set partial derivative of j with equal to theta not equal to 0, right? Let's see what this means. Now, taking derivative of this quantity with respect to theta naught, again the chain rule applies. So, if you treat this as x square, these two terms, this term and this term will stay the same. But when you take the derivative of the inside quantity with respect to theta naught, this first term will give no result. This will just give 1 and this term will give 0. So the only term which will actually survive is if you take 1 by 4 common, the only term which will survive is treating it as y equal to x square. So it will be 2x because the derivative of the inside quantity with respect to theta naught is just equal to 1. So it will actually be multiplied by 1 plus 2 times theta 1 x2 plus theta naught minus y2 plus 2 times theta 1 x3 plus theta naught minus y3 plus 2 times theta 1 x4 plus theta naught minus y4. And now this whole quantity we need to set this equal to 0. Now when you plug in the values of theta 1, sorry, x1, y1, x2, y2, x3, y3 and x4, y4, you will get the second equation as 10 times theta 1 plus 4 times theta naught minus 14 is equal to 0. So this is my second equation. And now we have a classic case of two equations and two unknowns. And it turns out that when you actually solve this, you can just multiply by 3 and subtract. That will give you the value of theta naught. So it turns out that when you solve it, you get theta, you get when you solve these two equations, you get theta naught is equal to 1.5 and theta 1 is equal to zero point 0.8. This is the final value which you obtain. So the best separator which you obtain is actually, it looks like this. The form which the best separator takes is y is equal to theta 1 x plus theta naught, right? So this will lead to y is equal to zero point 0.8 x plus 1.5. Isn't this beautiful? Because we obtained a closed form solution here, which we did not obtain for the logistic regression, right? When we minimize the cross entropy loss, there was no analytical solution. But now we analytically solved it completely and directly got an answer in front of us. When you plot this with the actual data, this line actually looks something like this. Let me actually plot it once more. So this was my first point, this was my second point, this was my third point, and this was my this was my third point, and this was my fourth point. So when you plot this line, and I really encourage you to plot it, it looks something like this. It kind of passes through the middle of these points, and this is my best hypothesis. Y is equal to zero point 0.8 x plus 1.5. This is wonderful since now use formulating machine learning as an optimization problem. We found the values of theta 0 and theta 1 which led to the uh, minimum least square loss or minimum squared loss. This is what is called as ordinary least square. It's as simple as that. And you just did it yourself for two dimensions. For now, there is no need to think of matrices. This is ordinary least square. This is the ordinary least square solution, and it's an analytical solution uh, which gives us the exact answer. I want you to understand how simple it is to come up with this solution. So next time when you think of ordinary least square, don't no need to think of complex matrices. Just think that you wrote the loss function and then you just took derivatives to minimize the loss function. You got two equations and you got two unknowns. You solved them to get theta 0 and theta 1 and you got the optimal solution. That's it. Okay, now we look at the traditional approach which many courses take to teach ordinary least square. So This will involve the use of matrices. And the reason this approach is taken is because currently I showed you with respect to 4 points, right? And I showed you in 2 dimensions. But what if we have more dimensions, and what if we have more points? So can the ordinary least square solution be obtained in terms of a general formula for any dimensions and for any number of points? So now let us look about that. Similar to the j function which we wrote here, this j, look at this. This was the objective function, right? Now I'm just going to replace 4 with n if we have n number of points. And here also, instead of just theta 1 and theta naught as two scalar values, we will have a vector theta and a scalar theta naught, because we have to consider the case for any dimensions. So now let us see ordinary least square with matrices. And finally, we'll also have a section on how what we did with matrices corresponds quite well with the analytical solution which we obtained over here. Okay, so now let me write the function j for any number of points and for any given dimension. So j will again be a function of theta and theta naught, and it will be the summation of the guess minus actual for all my data points. It's actually exactly same uh, to what we wrote for the two dimension case above. The only difference is that we have n points here, and the another difference is that theta will be a vector of d dimensions, theta 1, theta 2, theta d, since we can be in any d dimensional space. Even here, very similar to what we did before, we want to find theta star and theta naught star, basically, which minimize j. As I'm proceeding through this derivation, you will notice that this is exactly similar to what we did in the two-dimensional case. We saw that we wanted to find theta 0 and theta 1 which minimize j, and then we took derivatives. We are going to do the same thing here, but before that we need to do some tricks. And these tricks I already showed you in the logistic regression. The trick number 1 which we are going to do, it is called as the augmentation trick. Uh, so if you look at x, which is the input vector, it currently looks something like this. Let's say I'm again in the two-dimensional space, but I have n number of points. So the x will look like this. This is my first data point. No, this is the first. This the column is my first data point. So the column is my first data point, and different columns are my individual data points, and overall there are n data points. So the last column is my nth data point, and the y will be is equal to y1 to yn. So I am taking 2 by n here, because there are I am assuming that x has two dimensions and the y has one dimension, just for the sake of simplicity. The case which we considered here was even simpler because x just had one dimension. Anyways, the augmentation trick which I want to show you is what we saw earlier also. Instead of writing it like this, we will add a column of 1 to x. So basically the w, which is my augmented, it's also called as the weight matrix. It will look something like this. It will look like, initially, I will have a vector of ones. So 1, 1, 1 up to n. So my first x2 1, and then finally it will be x1n and x2n. So this is now the weight matrix. So you see what we have done here. The X matrix which was here, we have just taken a transpose of it. So here the column was a data point, right? Here each row, so each training example is a row. So essentially the W matrix is just the first row will be the one and then the first data point. Second row will be one followed by the second data point. Now think about for this case which we took where the x coordinates were 1, 2, 3, and 4, right? So in this case the W matrix would simply have been this. There are 4 points, so 1, 1, 1, 1. The first point is just 1. Second point x is 2, 3, and 4. That's it. This is how the W matrix would look like for the case which we had before, the one dimensional case. What I've showed you here is for 2 dimensions. For 3 dimensions, it will be there will be one more parameter here, so there will be 4 columns. So that's it. The weight matrix is just this kind of a transformation trick. And the reason we do this trick is because we want the theta naught to be embedded within the theta itself. So now this is W and my theta and theta naught won't be separate. I'll have a combined theta matrix which will be theta 0, theta 1, dot 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 theta D. So in this case, it will be theta 0, theta 1 and theta 2. And in our case of one dimension, it will just be theta 0 and theta 1 because those were the only two quantities unknown. Remember here, those were the only two quantities which we needed to figure out. And then last thing is the t vector. The t is just going to be y transpose. So basically whatever labels you have, you just y1 1 dot 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 yn1 or yn. That's it. Basically you just have a column vector of the labels. And in the case of this thing, so this the W matrix I already showed, the theta matrix I already showed. The T matrix for our one dimensional case would be just the collection of Y values. So it will just be a collection of so the Y values are 2, 3, 5, and 4. So this will just be 2, 3, 5, and 4. Okay. Now I am going to show you um how we can write the J function in terms of matrices, especially in terms of the three matrices we looked at above. So the J function is, if you look at it in vectorized format, it looks like this, right? Where we take every individual point and then we take the guess minus actual for that point and then we take a summation over all points. The question or the task which we have before us is now how to represent J in terms of W, which is the weight matrix, theta, and the T, which is the label matrix. Remember, which we already saw the W, which is the augmented weight matrix. We saw the theta matrix, which is just adding a theta naught, and we saw the T matrix, which is just a vertical matrix of all the output labels. It turns out that there is a very simple form of representing J. We don't even need to worry about the summation. It turns out that J of theta in matrix format is just this: W theta minus T transpose multiplied by W theta minus T. Now W theta minus T has a very simple meaning. W is just our excess basically with that augmented one matrix multiplied by theta. So this is just our predictions and it's dimensions will be n by 1. This is just our actual values. Since it's a collection of the y labels, this dimension will also be n by 1. So the transpose dimension will be 1 by n. This will be n by 1. So the j theta will be a scalar loss, since 1 by n into n by 1 will give a dimension of 1 by 1. Now you all might be wondering that how is this possible, and how come this is the same as this j, and we will come to it. We have a final section devoted to the equivalence between the matrix representation and what we did in the analytical solution above. There you will finally learn why the matrix form is so compact, and why it is exactly similar to what we did in the analytical solution. But for now, just stick with me here. And we still have not done the next step yet. Remember, we took gradients, right, with respect to theta 1 and theta naught. So now we have to find the theta, or find theta star which minimizes j, correct? So we have to find theta star which minimizes j. So we will take the derivative. We will take the derivative of j and set it to 0. Remember that theta is a collection of theta 0, theta 1, dot dot dot, theta n, theta d. So when we say derivative of j with respect to theta, it's usually called a gradient of j, and it is just a vector where you first take the gradient with respect to theta 1 dot dot dot, and then you take the gradient with respect to theta d. In the case of the two dimensions which we saw, or rather the one dimension case, we did exactly the same. We took two gradients, remember, theta 1 and theta 0. So in the case of the one dimensional case which we saw, this actually translates to derivative with respect to theta 0 and derivative with respect to theta 1. So this is gradient of j. So all we need to do is take this gradient of j and set it equal to 0. And remember, my j is this 1 by n. Now your question would be, how do I take the gradient of this matrix with respect to theta? And if you have not studied matrix algebra, it's fine. Let me give you an intuition for it. Uh, okay, so imagine that this is just y equal to x square, because x transpose x is just modulus of x square, right? What will you do? You will just do 2x, right? This is exactly the first step here. You will first do 2x, and then you will take the derivative of what's inside, correct? So grad, it turns out that first you bring the 2 out, so it will be 2 by n, 2x. So a w theta minus t, and then you go inside and then you take the derivative with respect to theta. So then a w transpose will survive. So it turns out that the derivative or the gradient of j with respect to theta is this quantity. Looking at the dimensions of this is d by n, and the dimensions of this is n by 1. So the dimensions of the gradient j, or gradient of j, will be d by 1, which is exactly similar to the dimensions of theta. So this seems to be correct. And now we want to set this equal to 0. If we want to set this equal to 0, this actually means that w transpose w theta minus t is equal to 0. This actually means that w transpose w theta is equal to w transpose t. Now there is something called as the inverse of a matrix, and when you multiply it by the matrix, it gives the identity. So let me multiply both of these sides by inverse of a matrix. Theta is equal to w transpose w inverse w transpose t. So this will just be the identity matrix, so it will kind of cancel out. So my final theta, or the theta star, which optimizes the least square solution, is this. And this has been completely obtained in an analytical format. This is a beautiful solution, right? Because now I am telling you that you give me points in any dimension, not just one dimension, but you give me these points in three dimensions, four dimensions, five dimensions, any dimensions, and you give me any number of points. Basically, I don't even need to do any calculations. Um, I'll just take this matrix which has been obtained, and I will get the final answer. That's why this is the beauty, what the MIT lecture calls. This is the beauty of the closed form OLS solution. This is the beauty of the closed form OLS solution. And the reason it's said like this is because it's usually very rare to get closed form solutions in machine learning. It's not that easy to obtain. This solution does have two main issues. First thing is that, what if, so all matrices are not invertible. So what if W transpose W is not invertible? And I'm deliberately not going into these details. And second, this computation time may take too long. Computation time may be very high, because if the number of data points increase, to take the inverse is actually a very computationally expensive operation. Before going any further, first of all, what I want to show you now is the equivalence between the vector form, which we did over here, and the matrix form at every step of the process. So let me actually spend some time on that so that you don't feel like some magic has happened here. And then finally we will compute the matrix solution and check it with our answer. Okay, so now what I want to do is this. Let us compare the vector operations which we did earlier for every individual point, and then this magical matrix thing which we did in the previous section. And let me prove it to you why all these things are correct. So first thing we will start with, which you might be thinking, is where did this function come from? Where did this W theta minus T and all these things come from, right? Okay, so let us compare. So J of theta, which is our objective, let us first see for vector what it was. Remember, we wrote it down very clearly for the vector operation, and this was the J of theta, this quantity here. So let me write it down again. Okay, so let me write down this J of theta again, what we already did. And we wrote that it looked something like this, correct? Theta 1 x1 plus theta naught minus y1 square plus theta 1 x2 plus theta naught minus y2 square plus theta 1 x3 plus theta naught minus y3 square plus theta 1 x4 plus theta naught minus y4 square. So this is the vector. So this is the vector version. Now let us look at the matrix version of J of theta. As we saw earlier, the matrix version of J of theta is something like this: 1 by n W theta minus T transpose W theta minus T. So let me write it down here again. So this will be 1 by 4 W theta minus T transpose W theta minus T. So once and for all, let me write down the W, theta and T for the case of this problem which we had taken. So W is just the augmented matrix. We have four data points. The first data point, we augment a 1 and the input is 1. The second data point, the input is 2. Third data point, the input is 3. Fourth data point, the input is 4. So it will be this, or in terms of x1, x2, x3, x4, it will just be this. x2, 1 x3, and 1 x4. Correct? My theta will be equal to theta theta 0 and theta 1, and the t is just a collection of the y labels. So it will be y1, y2, y3, y4. So now let us evaluate this quantity, this w theta minus t transpose into w theta minus t. So then it will be something like 1 by 4, uh, 1 1 1 1 x1 x2 x3 x4. This is w. Theta is theta 0 theta 1 minus y1 y2 y3 y4. So this is w theta minus t, and this is equal to, so if you look at this multiplication, it will be, so this has 4 rows and 2 columns, and this has 2 rows and 1 column. So the final vector will have 4 rows and 1 column, and in each row you will multiply the first value and the second value. So the first row will be theta 0 plus theta 1 x1. So, and you subtract then by y1. So w theta minus t will be just equal to, so this is w theta minus t, that will just be equal to theta 1 x1 plus theta naught minus y1, theta 1 x2 plus theta naught minus y2, theta 1 x3 plus theta naught minus y3, and theta 1 x4 plus theta naught minus y4. This will be w theta minus t. And now if you do 1 by 4 of this quantity, theta 1 x1 plus theta naught minus y1, theta 1 x2 plus theta naught minus y2, theta 1 x3 plus theta naught minus y3, theta 1 x4 plus theta naught minus y4. You have to take the transpose of this w theta minus t transpose, and you have to multiply it by the same quantity. Multiply it by the same quantity. So x transpose x, if anyone has done these operations, it is just the summation whole square. So if you actually do this multiplication, you will get the answer equal to 1 by 4 theta 1 x1 plus theta naught minus y1 square plus theta 1 x2 plus theta naught minus y2 square plus theta 1 x3 plus theta naught minus y3 square plus theta 1 x4 plus theta naught minus y4 square. And now if you compare it with the vector quantity, look at this. This was the vector quantity, and this is the scalar or the matrix quantity, and both of them are exactly similar. That's why this matrix multiplication actually works. This matrix representation which we have over here, it might look a bit complicated, but if you write it down on a piece of paper, it really works. So this is the comparison which we did for J. Now let us look at the comparison for gradient with respect to J. So gradient with respect to J, and we saw that for the case of the matrix, it was equal to, let us see what it was. Uh, this we saw that the gradient of j was this value. So let me write it down and let's compute this value. So it was 2 by n w transpose w theta minus t. So if you compute it for the case which we have, and if you replace n, w transpose will be 1 x1 1 x2 1 x3 1 x4, since it's a transpose, and w theta minus t we have already seen, it's this vector. So I'm just going to write theta 1 x1 plus theta naught minus y1 dot dot dot. Now, if you do this multiplication, you will get that this is equal to 2 by 4. It will have two rows. The first row will be theta 1 x1 plus theta naught minus y1 plus theta 1 x2 plus theta naught minus y2 plus similarly for y3 and similarly for y4. This will be the first row. The second row will be x1 times theta 1 x1 plus theta naught minus y1 plus x2 times theta 1 x2 plus theta naught minus y2 plus x3 times similarly for theta 3 and plus sorry for x3 and similarly for x4. These are the two rows. And why do we have two rows? Because the first row corresponds to the derivative with respect to theta naught, and the second row corresponds to the derivative with respect to theta 1. Now let us go back and see what we had for the vector operation. So look at this. When we did these computations, look at what we had for gradient with respect to theta naught. If you take this 2 out, it will be theta 1 x1 plus theta naught minus y1 plus theta 1 x2 plus theta naught minus y2. Similarly for x3 and x4. This is exactly what we are getting here. Look at the first row. The first row is exactly what we had also obtained. Now let us look at gradient with respect to theta 1. Gradient with respect to theta 1 is just x1. So if you take this 2 out, x1 into theta 1 x1 plus theta naught minus y1 plus x2 into theta 1 x2 plus theta naught minus y2. Similarly for x3 and x4. And if you look at the second row here, look at the second row. X1 into theta 1 x1 plus theta naught minus y1 plus x2 into theta 1 x2 plus theta naught minus y2, etc. It's exactly the same as the calculation which we had done before. So essentially what I want to illustrate here is that the two main quantities which we looked at for the matrix, although they seem initially magical, but if you work it out on a piece of paper for this gradient and for the representation of the loss function itself, this. So what I'm marking with star, this is J and this is gradient of J. What many courses do is that they just start with these quantities and students think of it as magic, like where do these quantities appear from? But if you actually initially do the computation on your own, like we have done on this piece of paper or the whiteboard, you can actually compare the matrix value with what we have obtained and you can see that it is exactly similar. That is why the matrix solution works. Now let us actually compute the matrix solution which we had. The matrix solution theta star, the matrix solution and here I'll also teach you how to compute the inverse of a matrix. Let me use a different color here because we have used so many other colors. The matrix solution, which is theta star, is equal to W transpose W inverse W transpose T. Correct? Okay, so let's see. What is my W? My W is just, we have already written it over here. My W is this. 1 1 1 2 1 3 1 4. Correct? So then W transpose will be 1 1 1 1 1 2 3 4. So W transpose of W into W will be 1 1 1 2 1 3 1 4 multiplied by 1 1 1 2 1 3 1 4. If you do this multiplication, you will obtain a 2 by 2 matrix. So the trick is that this has 2 rows and 4 columns, and this has 4 rows and 2 columns. So the final matrix size will be the first value from here and the second value from here. So it will be 2 by 2, and it will be 4, 10, 10, and 30. Okay. And then, so this is W transpose W, and W transpose T is just 1, 1, 1, 1, 1, 2, 3, 4 multiplied by the Y values. And the Y values are, I think they are 1, 2, 5, and 4. Let us see. Yeah, the Y values are 2, 3, 5, and 4. So let us replace these Y values as 2, 3, 5, and 4. So this is W transpose T. Again, the first is 2 by 4, second is 4 by 1. So the final value will be 2 by 1. Two rows, one column. And if you calculate this, this will turn out to be 14 and 39. Okay. So this will turn out to be 14 and 39. So W transpose W inverse W transpose T will just be 4, 10, 10, 30 inverse into 14 and 39. This is our final answer for theta, theta star. One thing which I want you to recognize, which is very, very nice actually, is that do you recognize these numbers? Have you seen them somewhere? Where have you seen 14, 39? Have you seen 1439 somewhere? Let us go back to our analytical calculations and let us see the two equations. Look at the equation number 1. 30, 10, 39. 10, 4, 14. Now let us go here. 30, 10, 39. 10, 4, 14. Same numbers. Basically, this formula, what we are doing here is that we are solving a system of equations. We are solving a system of equations of two equations in two unknowns. And that's why we have this inverse term here, because whenever you solve a system of equations using matrices, you have to take an inverse. And that's why all these terminologies here are exactly matching the equations which we had. This is another proof that this matrix answer is actually working, because we exactly arrived at the same numbers ourselves. Now here is how you calculate the inverse of matrices. If you have a matrix A is equal to A, B, C, and D, then the inverse of this matrix A inverse is given by 1 upon uh, determinant of A, which is AD minus BC times D minus B minus C and A. You can check it out for yourself by multiplying A inverse into A. It will be the identity matrix. This is also called as the determinant of A. And if this is equal to 0, it means the inverse does not exist. It's also called as the singular matrix. So now let us calculate the inverse for this matrix which we have obtained over here. So similar to this, then the formula will be 4, 10, 10, 30 inverse will be 1 upon A into D minus B into C, which is 120 minus 100, which is 20. Then the first will be D, which is 30. This will be minus B minus 10 and 4. So if you compute this, this will be equal to 1.5 minus zero point 0.5 minus zero point 0.5 and zero point 0.2. And in the final solution, now we have to just multiply. So theta star will be equal to this inverse which we have obtained, minus zero point 0.5 minus zero point 0.5 and zero point 0.2 multiplied by 14 and 39. multiplied by 14 and 39. So if you do this computation, you will obtain theta star as 1.5 and zero point 0.8. Okay, so we obtain that the optimal theta 0 is 1.5 and the optimal theta 1 is zero point 0.8. So the optimal hypothesis is y equal to zero point 0.8 x plus 1.5. Do you remember where you have seen these numbers 1.5 and zero point 0.8? Let us go back to our analytical solution and let us look at the numbers which we had obtained. Okay, so here look at theta naught which we had obtained, it was 1.5 and theta 1 was zero point 0.8. So the optimal hypothesis which we had obtained from handwritten calculations is y equal to zero point 0.8 x plus 1.5. This is exactly the same hypothesis y equal to zero point 0.8 x plus 1.5 which is given to us through using this formula. Isn't this amazing? We got the exact same answer using our analytical solution and using this matrix formula. One thing I want to show here is that that's why this writing things in form of matrices makes things very compact. We did so many steps to reach the analytical answer earlier, but if you knew this formula, all you needed to do was just put in w, put in t, take this inverse and then obtain the final answer. That is the beauty of the closed form ordinary least square solution. It directly presents you with this formula. There are some complications which arise. So for example, if it's difficult to take the inverse here, what to do? What if the matrix is singular? So what if the determinant is 0? Then if the size of the matrix is of the order n, usually taking an inverse is a very computationally expensive operation which takes of the order n cube. So what to do for large data? If we have 1 million data points, how do we get the inverse? It would become very difficult, right? So we will look into these considerations further. But today's lecture, I want you to appreciate that OLS or ordinary least squares is not difficult at all. Without knowing anything about matrices, we obtained at the final answer on our own by just taking the derivatives. Matrices just makes it easy because what if you had huge number of points? What if you had higher dimensions? How would you do that on a piece of paper? It will be difficult to do these calculations. In that case, it's much better to stick with matrices. Look at this formula for j of theta for a gradient of j. And then finally just use this formula for the best theta star. W transpose W inverse into W transpose T. We also showed the equivalence between matrix and the vector operations for j and for gradient of j. It's exactly the same as what we did in our handwritten calculations above. So thank you everyone. This brings us to the end of this lecture. This was a pretty long lecture, but it was needed because I wanted to introduce you to OLS in a correct manner. What many courses do is they first of all don't even show the hands-on demo. They directly go to this matrices. They directly start with these formulae. And then it's very difficult to know where these formulae come from. Do they actually work? But if you have done this yourself, then you know that these formulae make sense. What I would highly encourage for you after this lecture is you yourself do these calculations for maybe some different data points and then you compare it with the matrix formula and see whether you are getting the same answer or not. That way you will never forget ordinary least squares. In fact, this question may be asked by interviewers when you look for ML jobs. So try to master this lecture and I hope you understood it since my aim is to always teach you from basics. I'll be uploading these notes where I show all these calculations for your reference at the end of the YouTube video. Thanks a lot for supporting us throughout this journey. The next lectures will be even more interesting where we'll further look at regression with regularization. Up till now, we did not consider regularization, right? We will look at that in subsequent lectures. Thank you so much, everyone.